So we have physics Ph.D. qualifying exam practice problem number 17. This is in the domain of statistical mechanics. So let's begin. Consider a classical gas of n identical non-interacting relativistic particles combined in a cubic box of volume V. The single particle Hamiltonian is h of p equals c times absolute value of p, where c is a constant velocity. Part A, derive the microcanonical density of states omega of E Vn for the system. Part B, from the entropy S of EVn equals k sub b ln omega, derive the equation of state. For part C, construct the canonical partition function and verify that the thermodynamic relations agree with microcanonical ensemble and the thermodynamic limit. And for part D, determine whether equipartition theorem holds for this system and justify mathematically. So I'll go over this rather quickly because you have the setups as a reference with the answers. Okay, so density of states in ensemble equivalence, part A, relativistic classical ideal gas. Here's our Hamiltonian for canonical density of states. Here we have our phi equals the following 1 over n factorial h to the 3n of this entire integral here. And the position integral gives v to the n. For momenta d cubed, here p sub I equals 4 pi p sub I squared d p sub I. So phi of E equals v sub n over n factorial h to 3n, 4 pi to the n. And then we have the integral over this region where the sum of c p sub I is less than or equal to E. And then we have this capital pi here where the product from I equals 1 to n of pi sub p sub I squared dp sub I. We're going to let q sub I equals c p sub I, so dp sub I equals d q sub I over c, and then the following p sub I squared dp sub I equals this q sub I squared d q sub I over c cubed. Thus we could say our phi of E equals v to the n over n factorial h to the 3n, 4 pi to the n over 3n. And then we have our integral here over this region where the sum of q sub I is less than or equal to E. And then we have this product here of this I, q I squared d q sub I for this capital pi. Moving along to the second component of this. See if this holds. Let me take this. Sorry about that. So, so using the Dirichlet integral here, so using that integral, we're going to get that capital gamma of 3 to the n over capital gamma of 3 to the n plus 1 e to the 3n. And since gamma of 3 equals 2, that phi of E equals v to the n over n factorial h to the 3n, 8 pi over n over c to the 3n, e to the 3n over capital gamma of 3n plus 1. So the shell density is capital omega of E equals this partial derivative of phi with respect to E. So we're going to wind up with that capital gamma of E equals v to the n over n factorial h to the 3n times 8 pi to the n over c to the 3n times e to the 3n minus 1 over capital gamma of 3n. Okay, so that's part A. Moving along now to part B. For part B, they want to know from the entropy S of EVn equals k sub b natural log of capital omega, derive the equation of state. So for part B, entropy and equation of state, we're going to use S equals k sub b ln capital omega. keep only thermodynamically dominant terms, so that S is approximately equal to, case of B, bracket, n ln V plus 3n ln E plus the terms independent of EV, close bracket. So then 1 over t equals this partial derivative of S with respect to E at Vn. That equals 3n case of B over E. So E is equal to 3n case of BT. And also P over T here, 3 over P. Also P over T equals this partial derivative here, S with respect to V, E comma N. That equals nk sub B over V. So PV equals nk sub BT. And combining with E equals 3nk sub BT, P equals E over 3V. And part C, what they want us to do is construct the canonical partition function Z NVT and verify that the thermodynamic relations agree with the microcanonical ensemble and the thermodynamic limit. So now for part C. Okay, so part C, canonical partition function. The one particle partition function is here for Z sub 1 equals V over H cubed. And then you have the integral here, sorry about that, D cubed P e to the negative beta C, absolute value of P. Using spherical coordinates, using spherical momentum coordinates, Z sub 1 equals V over H cubed 4 pi, integrate times the integral 0 to infinity, P squared e to the negative beta Cp dP. So since here we have 0 to infinity, P squared e to the negative alpha P dP, that equals 2 over alpha cubed when computing that. So then Z sub 1 is going to equal 8 pi V over H cubed C cubed beta cubed. And for n identical particles, Z sub n equals Z sub 1 to the nth over n factorial. That equals 1 over n to the factorial times the following in this quantity, 8 pi V over H cubed C cubed beta cubed raised to the n. So we could say our energy here, that's a negative D ln Z sub n with respect to this derivative, this partial derivative here with respect to this negative partial derivative with respect to beta, that equals positive 3n over beta. So E is 3n k sub B over T. And our pressure here, P equals k sub BT, times this partial derivative here of ln Zn, so that D ln Zn over dV, that's partial T comma n. That equals nk sub BT over V. So we get PV equals nk sub BT, and the canonical and microcanonical results, they tend to agree. And for letter D, determine whether equipartition theorem holds for this system and justify mathematically. So for letter D here, for equipartition, the usual quadratic equipartition theorem does not apply because H equals C times absolute value of P is not quadratic in momentum. However, the generalized equipartition identity gives the following: this expected value of P, alpha partial derivative of this H, so dH dP alpha, that's partial derivative, expectation value of that equals k sub BT for each Cartesian momentum coordinate. So summing over the 3 momentum components for one particle, this expectation value of P dotted with the del operators of PH, that equals 3 k sub BT. However, what we get here is this P dotted with del operators of P times this C times absolute value of P. That equals C times the absolute value of P. So the expectation value here, that's equal to 3 k sub BT, and the usual k sub BT over 2 per quadratic degree of freedom does not hold, but the generalized equipartition theorem does. Okay, so that's all for this one. Thank you very much and have a great day.